Here we're doing question 1 out of 7 questions. Here we're just trying to find the max or the min, but they already gave us the derivative. Okay, you can see there's nowhere that this derivative is going to be undefined. So we just want to check, where is this derivative going to equal 0? It's already factored nicely, so we can see x equals 0, x equals 2, and x equals -1. Those are our 3 critical numbers. Now we can test in between. Let's start by plugging in -2. F prime of -2 is equal to 128. So the value of the derivative when x is -2 is going to be positive. So that's why we have a positive right there. Now let's plug in -1/2. We get 125 over 64, but it's positive. Now let's plug in a 1. We get -4, so that's negative. Now let's plug in a 3. We get 48, so that's positive. Now what does this mean? If your derivative is positive, then that means your function is increasing. So we're going to be increasing on those intervals. If your derivative is negative, it means your function is going to be decreasing. So we expect to get a max when x is 0, and we expect to get a minimum when x is 2. And that's it. For this question, we were just trying to find where the max occurs and where the minimum occurs. Okay, we're doing question number 2 out of 7 questions. They're asking us how many zeros does this function have? And what they're giving us is they're telling us there's a max at this point, there's a min at this point, and a max at this point. So we're going to use that information. It's like a little puzzle. We have a relative max at 2, 4. So that means our function is going to turn around at that spot. There's a min at 4, -3. Again, our function is going to turn around at that spot. And then a relative max at 6, -1. So we're going to turn around at that spot. Well, because there are no other critical numbers, if we were to turn around and create another 0, well, we would also be creating another critical number. So you cannot turn around. Since we know we cannot turn around, we're just going to connect the graph here, and connect the graph here, and then this one's just going to have to go down. How many zeros are there? There's 1 0 right here, and there's 1 0 right here. Again, on the right side, it's just going to go down. So the answer to this question, there are 2 zeros. Okay, this is question number 3 out of 7 questions. For this one, they're just asking, is this a local minimum or not? We know it's not an absolute minimum because the function goes down forever. But how about a local minimum? Is it a local minimum? Well, in order for this point to be a local minimum, it would have to be the lowest value inside of any interval that contains that point. So I would say yes, this is a local minimum. How about this one? Is this one a local minimum? Well, a local minimum cannot happen at an endpoint. This point is the endpoint, so you cannot put it inside of an interval that contains that point because it's at the end of the interval. So the answer to this one is no. Okay, this one wants to know how many critical numbers does our function have on the interval from 0 to 5. Now they tell us that the derivative is cosine, so the original function was some kind of sine function. In this situation, our critical numbers are just going to be where this derivative is equal to 0, because there's nowhere that that derivative will be undefined. Now we're going to use our calculator to find the answer for us. We're looking at the interval from 0 to 5. So let's get our graphing calculator. Okay, we want to get solve. So we go to F2. Very first choice is solve. We want to solve it for x. So we're going to do comma x. Don't forget the right parentheses. We'll go back inside. And now we just need to put the equation. We want to see where cosine of 3x is equal to 0. Now the problem with this is that we're going to have an infinite number of solutions. So we want to evaluate it from 0 to 5. So we're going to push the evaluate button, and then we're going to say from 0 to 5. The less than button is blue and then 0. Now most of the newer TI-89 graphing calculators will work if you just push this. Push enter. Now this graphing calculator says that there's a syntax error, and that's because it's using an old operating system. That's okay. There is a way to do it. We just want to say when x is greater than 0 and when x is less than 5. The greater than button is going to be blue and then the period. To get and, I usually just go to calculator. If you go to the A's, the second choice is the and. So you can see that we are evaluating it when x is greater than 0 and when x is less than 5. Push enter, and it gives us all the answers. You get 3 pi halves, you get 7 pi 6. Now there's some more answers over here, so we got to push up, and then we push right. And it shows us the rest of the answers. You got 5 pi 6, pi over 2. You need to see more of the answers, so we'll push to the right again. The last one is pi over 6. So to answer this question, we can just say that there are 5 critical numbers on that interval. Another way we could do it is just to graph this from 0 to 5 and see how many times it crosses the x-axis. In order to graph it, we're going to do green, y equals, and then we're going to push enter so we could type in the function. Push enter again, and there's our function cosine of 3x. Now that's the derivative, and we just want to know where is the derivative equal to 0. So we just want to see where is the graph touching the x-axis. We want to do it on our interval from 0 to 5. So before I push graph, I want to go to window, that's the diamond and F2, so that I can go from x equals 0 as my starting value, and then x equals 5 as my ending value. Now I can graph it, that's the diamond and F3. And then you can just look to see how many times the graph crosses the x-axis. If it's difficult to see, you can go back to the window. You can change the y value a little bit. Let's go from -2 to +2. And now when we graph it, it's a lot easier to see. It crosses 1, 2, 3, 4, 5 times. Okay, this is example number 5 out of 7. You'll notice that they gave us the graph of the derivative. It's not the graph of f. I want you to notice that this graph is equal to 0 at these 3 values. So those are going to be our critical numbers because that's where our derivative is equal to 0. When x is b, c, and d. Okay, I want you to notice that our function is negative before you get to b. So we're going to put negative for our derivative. It's also going to be negative between c and d. So we can put negative for the derivative between c and d. Then you'll notice our derivative is above the x-axis, so that means positive between b and c. So we can put positive. We're also positive between d and e. So we'll put positive for the derivative over here. Now what that means for our original function is that if our derivative is negative, our original function will be decreasing. And where our derivative is positive, our original function is going to be increasing. So we're looking for a relative max or a relative min. We can see there's a relative max when x is c, and we get a relative min when x is either b or d. And that's it. Okay, here it says, which of the following is an equation of a curve that intersects at right angles every single curve of this family, where c is just a constant. Okay, because this is -1/8 x to the 4th, x to the 4th looks something like this. It's a little bit flatter than x squared, and the negative flips it upside down. So it's going to look something like this. And the plus c just moves it up or down. That's really not that big of a deal. But we need one of these functions to intersect at right angles. So you should have right angles at the point where they intersect. So what we need is we need the slope of this to be perpendicular to the slope of one of these. Remember, the slope is just the derivative. So let's check first. What's the derivative of this one? There you go. You can reduce the 4/8, it becomes 1/2. Now let's write this as a single fraction. Okay, now we're going to look at the slope of these functions, and we're looking for the negative reciprocal. So we need the derivative of one of these to be 2/x to the 3rd. Because that would be the negative reciprocal of -x to the 3rd over 2. Remember, if the slopes are perpendicular, they're going to be negative reciprocals of each other. Let's check the derivative for each of these functions. Okay, before we do the derivative here, we got to rewrite it. Okay, our derivative is going to be, and we can rewrite that as 1/x squared. But that's not the same as 2/x to the 3rd. For the example in the middle, the derivative is just going to be negative 2x. Again, that is not 2 over x to the third. For the third one, we want to rewrite it. The derivative is going to be, and we can rewrite this as 2 over x to the third. That's exactly what we were looking for. So our answer is going to be the third function. Let's look at that on a graph. Okay, our first function in red is negative 1 over 8x to the fourth. And then our other function is y equals negative 1 over x squared. That'll be the blue one. You can see where they intersect. It does look like it's perpendicular. But let's add some other numbers in here. Remember, it was plus c, so our c can be any value. Let's put plus 1. Still looks like it's perpendicular where it intersects. Let's try minus 1 just to see what it looks like. Yes, it still looks perpendicular at the point of intersection. How about minus 3? Yes, it still looks perpendicular at the point of intersection. Okay, this is our last example. It's question number 7 out of 7. Below, they give you a graph of the derivative. Again, be careful. That's not the graph of the original function. That's the graph of the derivative. We can use that graph to fill out our chart. When your graph is above the x-axis, it's going to be positive. So that means our derivative is positive whenever you're above the x-axis. So we're going to be positive in all of those regions. When your graph is below the x-axis, it will be negative. So that means our derivative will be negative in the blue shaded regions. So our derivative is going to be negative between b and c, and our derivative will be negative between e and k. Now, what does that mean about our original function? Well, if your derivative is positive, it means that your original function is going to be increasing. Now, if your derivative is negative, that means your original function is going to be decreasing. So that's creating a max here and a max here and a minimum right here. Now, what does this tell us about our original function? Well, it tells you that you have a local max here and a local max there. And one of those 2 points could be an absolute max. It also tells you that you have a relative min here. It is possible to have an absolute minimum at one of these 2 points or the middle point. We don't know which one is the lowest point. Okay, over here we're trying to clarify that the endpoints could be an absolute minimum. So either of those 2 points could be an absolute minimum. So could the middle point. Here it also says that the endpoints cannot be a local minimum. So you cannot get a local minimum over here, but this is a local minimum for sure.